Good morning. Can you guys hear me?
Yes, sir. Good morning.
Good morning. I am going to start the class going to chapter 6, and I will be finishing chapter 6 today. We will be having a test next week, probably Wednesday. I am going to have a review session on Monday. So Wednesday we will have the test. Probably you can have it on Wednesday or Friday. All right. Okay, let me share my chapter 6 slide. Do you guys have any questions?
No, sir.
Can you see my chapter 6 slide page? I am going to go over instructional objectives and review what we have done. We try to explain homogeneous mixtures in terms of solutions. Solution is a general name for homogeneous mixture. We also look into various factors that affect the solubility of a solute, minor component, in the solvent, major component. Factors like structure of the solute and the solvent, like dissolves like, effect of temperature, effect of pressure, we talked about. Also how these solubility is affected by intermolecular forces, hydrogen bonding, dipole-dipole, and London dispersion. That's the term like dissolve like. This is the similar structures. Some structures are polar, some are non-polar. Polar compounds dissolve in polar. Non-polar compound dissolve in non-polar. That's the idea behind like dissolves like. We talked about the temperature of a solubility of a gas in a liquid. Temperature decrease the solubility. Therefore, you have to keep carbonated drinks. Once you open it, you have to keep it inside the refrigerator. Otherwise, carbon dioxide will escape quickly. We also talked about solubility rules for ionic compounds. We covered this material on chapter 4, solubility rules. There are rules that definitely say which ionic compounds are soluble, which are not soluble in water. Heat, as the temperature increase, heat increase. Most of the liquids and solid increase solubility. That means solute solvent get mixed up and form homogeneous solution as the temperature increase. This is one of the important section on chapter 6, concentration. We talk about mass by mass or weight by weight, volume by volume, mass or weight by volume, and molarity. These are the major concentration units. We also talk about ppm and ppb, which are similar to percent concentrations based on mass by mass or weight by weight concentration unit. We did a lot of calculations of factors, variable associated with weight by weight, volume by volume, weight by volume. We also did dilution problems, where we calculate the new molarity of a solution prepared from concentrated solution by adding water, adding the solvent. Water is our main focus. So we interconverted different concentration units. Explain how concentrated solution can be mixed with to make dilute solution. We use a volumetric flask. We talked about it. If you want to prepare certain molarity solution of certain molarity, you get the grams of the solute converted to moles and dissolve that in a 1 liter volumetric flask. You get one mole dissolve of any solute dissolved in 1 liter of water. It's 1 mole. Now, this is up to 11 we have talked about. Today I'm going to start with going over colloids and suspensions. There are 3 types of mixtures. One is the homogeneous mixture, which are true solution. Colloid is a homogeneous, similar to solution, a homogeneous mixture. Particle size is little larger than found in normal solution. Therefore, solute particles in a solution scatter light because they have larger surface area and particles are larger. That's what we call colloids. We're going to talk about this. Suspensions are even more larger particles than colloids. Therefore, they separate out from the mixture and deposit at the bottom of the beaker if you try to make a homogeneous mixture between certain water and solute with large particle size. We're going to talk about this. The last topic we're going to talk about is colligative properties. Colligative properties are properties of a homogeneous mixture. in a solution, which are dependent on number of solute particles. Colligative property definition is the number of solute particles. So most important properties is colligative properties, freezing point depression, boiling point elevation, and osmotic pressure. We're not going to talk about vapor pressure lowering. If you dissolve a certain solute in a solvent, normally vapor pressure decrease, lowering. Freezing point also lowered, depressed. Boiling point is higher. Osmotic pressure is a property when solute is used to make a solution, and that solution is separated from the solvent, pure solvent, by a semi-permeable membrane. There's a solvent pressure developed from the solution solvent side that pushes more water into solution of homogeneous mixture. It's called the osmotic pressure. We're going to look into this. We also, that's osmosis and semi-permeable membrane. I'm going to start the topic on colloids. A true solution in a beaker, like sodium chloride, which have small particle size, solute particle size. Particle sizes are less than 1 nanometer. Therefore, when you put them in a solution, when they are soluble, they break up in water and get dissolved in the solvent. The solution is transparent, light passes through. It's a clear, you can see through the solution. When a solute has between 1 nanometer and 1000 nanometer particle size, particle diameter. Diameter is the particle that's the diameter. When diameter sizes are between 1 nanometer, particle sizes are large, therefore they scatter light. A solution of homogeneous mixture. In some cases, when you pass light through, you can see scattering of light. Scattering of light. When particle size become close to 1000 nanometers, like a milk, you don't see light passing through. It becomes opaque. Opaque. Opaque means light doesn't pass through. The colloid is similar to normal solution, true solution. Normal solutions are called true solutions. But only difference is the light doesn't pass through solution, colloid solution. Colloid particles are stable dispersion. That means in the homogeneous mixture, they do not settle out from the solution. Suspensions settle out and get deposited on the bottom of the beaker. They are stable dispersion. We're going to talk about how large solutes get dispersed in a solvent to make colloids. Suspension, on the other hand, third category of homogeneous mixtures, have particle diameters greater than 1,000 nanometers and characteristic feature of suspension is they settle out. For example, muddy water, soil and water. The soil get deposited at the bottom if you leave it standing. So that's the third category of homogeneous mixture. There are three types of homogeneous mixture. Three types of mixtures. First is true solution. Second is colloids. Third is suspension. I am going to summarize what we talked about three types of mixtures. Solutions have between 0.1 and 1.0 nanometers. Diameters are in nanometers. Colloids are between 1 nanometer and 1,000 nanometers. Greater than 1,000 nanometers, the particle size become larger as you go from solution to suspension. The solute cannot be separated out by filtering the true solution or colloid. You cannot separate solute by using a filter paper. There are no filter papers that allows separation of solution, solute from the solution. Suspension, on the other hand, we can use a filter paper and solvent is separated from the whatever you are mixing. True solutions and colloids does not settle on standing. Suspension does. Behavior of light. True solution are transparent. The scattering of light when passing through a colloid solution is called Tyndall effect. Tyndall effect is seen, we are going to talk about it, when you pass light through a solution. You can, through the streak, see through the solution, the streak of light due to scattering of light from large particle size in solute with large particle size in colloids. Suspensions are kind of settled down at the bottom. Therefore, you cannot compare it to transparency or Tyndall effect. Let's look at colloids in detail. Gas dissolved in a gas never form a colloid. Gas particles are small. Something to become a gas, it has to be smaller. It's difficult to make large particles to become a gas. Therefore, there are no examples of homogeneous mixtures of gas in a gas that behave as the colloid. Gas in a liquid is called whipped cream. Example is a whipped cream. If you have a liquid, you stir up to dissolve, mix up gas. That's how make whipped cream. Whipped cream is opaque. Gas in a solid. Example is marshmallows. Marshmallows it's not liquidy. It's a solid. Whipped cream is a liquidy. So marshmallows are when you dissolve gas in a solid, it becomes a marshmallow type. Example is a marshmallow. Liquid in a gas. Gas is the major component. Like gas in a liquid, solid is the major component. Liquid in a gas means there's more gas than liquid. You get cloud formation. Liquid in a liquid, like milk or mayonnaise, they are liquidy. So liquid in a solid. Examples are cheese and butter. Butter is for oils in a solid mixture. Smoke is a solid in a gas. Solid particles dispersed in a gas is called smoke. We go over 6 types of 1, 2, 3 colloids. We're going to go through some examples later. Colloids show the property called Brownian motion. Colloid particles, because of the Brownian motion, they get dispersed. Brownian motion is shown here. If you put colloid particles in a medium, one of these mediums we talked about in previous slide, they get dispersed due to Brownian motion. They don't get separated into bottom or one place. Brownian motion or motion of dust particle. Example of Brownian motion is motion of dust particles in air. If the dust is in the air sample, there are dust particles. When you shine a flashlight, you can see that's not there. Scattering of light. When light scatters from dust particle, they show flashes. Now let's talk more about how colloid particles get dispersed in a medium. Normally we look into more solid in a liquid type dispersion, colloid dispersion. Why do colloid particles remain in solution despite their collision? That could lead to aggregation. Aggregation is clumping up, things coming together. Opposite of Brownian motion is aggregation. Colloid particles don't get aggregated. The reason is colloid particles have large solution layer. Large particles, they have a large solution layer. For example, in water, the large number of water is surrounding the colloid particle. This solution layer could be negatively charged on the outside or positively charged. Negatively charged or positively charged. When charged colloid particles, solvent layer has charge. For example, it could be negative when the water surrounds the particle, colloid particle. Therefore, they repel each other. Therefore, they don't aggregate. Therefore, solvent molecule play an important role keeping them from aggregation. We talked about Tyndall effect. When light is passed through, that's the colloid, that's true solution, that's true solution, that's a colloid. In here, light passes through without a scattering. That's true solution, that's colloid. Can you see the light scattering through the colloid large particles? That's called a Tyndall effect. This is one of the experiments we use to distinguish between true solution and a colloid solution. Smoke is dust in the gaseous. Serum is a blood sample with protein. Serum is liquid is called blood. That's a liquid part of blood which has proteins dispersed in the blood. They don't aggregate. Fog is when you have liquid in a gas. Fog also shows Tyndall effect. Let's talk about colloids and go through some problems. Which of the following is true of colloid particles? Particle size is 1 less than 1 nanometer. That's true. Scatter light, that's true. They are smaller than 1 and may, that's not true. None of these. That's not true. I said that's true. Smaller than is true solution. Therefore, B is the only correct answer. Which of the following is an example of a colloid in which gas is dispersed in a liquid? Whipped cream. Remember, whipped cream. Marshmallows is gas in a solid. Liquid in a solid. I forgot. Let's look at whipped cream is a gas in a liquid. Marshmallows is a gas in a solid. Fog is a liquid in a gas. Mayonnaise and milk, a liquid in a liquid. Cheese is liquid in a, or butter is liquid in a solid. Smoke is solid in a gas. We go on this. Gas in a liquid is whipped cream. And say D. Which of the following is a liquid in a liquid? Mayonnaise. Which of the following is an example of colloid in which solid is dispersed in a liquid? That's a jelly. Solid is dispersed. Which of the following factors affect the cause of solid particles to remain in the solution without settling. We talked about it. In colloids, they don't aggregate or settle down. They remain dispersed without settling. It's something to do with solvent. Colloid particles and solvent molecules are of the same size. That's not the answer. Particle size has nothing to do with getting dispersed. Colloid particles have large solution layer. That could be colloid particles and solvent molecules are same size. That's not true. Colloid particles have large solution layer. That's true, but end statement. True plus false make it false. The correct answer is have large solution layers. That can give a charge oppositely negative charge to the solvent layer surrounding the colloid particle or positively charged. They repel each other. Particles remain dispersed. Which of the following techniques can be used to decrease the stability of aqueous colloid solution? In water, which can affect the stability. The addition of solvent that has great affinity of B, that's not true. Water, increasing water doesn't break up the stability. The addition of an electrolyte. Sometimes when you add an electrolyte for milk, if you add acetic acid, that's the electrolyte, weak electrolyte. Lime or added to milk. That's how you remove milk proteins from homogeneous mixture of milk. Add acetic acid or lime. You get proteins, milk proteins, which are colloid particles, solid particles. The addition of solvent has great affinity and addition. That doesn't have the effect of decrease. This is correct, but overall this statement is not true. False, true become false. Neither of these. That's true. I didn't look into that. Addition of a solvent. That is an aqueous colloid solution. When you add another solvent which has more affinity for water, it kind of removes water layers from the colloid particles. Therefore, aggregation can both add in another solvent or adding the electrolyte. That's why the C is correct answer. Which of the following techniques can be used to decrease the stability of the aqueous? Let's look at that. Addition of electrolyte. That's true. Dilution is adding water. Not true. Both addition of electrolyte and the dilution of therefore this is by adding water, it doesn't decrease the stability. This second part of the statement is not true. Addition is true, but true and oppose become false. Therefore, A is the correct answer. Colloid dispersion differ from true solution in that colloid particles tend to settle. That's not true. They don't settle. Are large enough to scatter light. That may be difference between colloids and true solution. Are large enough to seen by naked eye. You cannot see naked eye or microscope. Colloid particles are too small. Therefore, only correct answers are large enough to scatter light. Colloid particles. B is the correct answer. What substance is a colloid? Manganese is, we talked about this, it's a colloid. Dental filling is a solid in a solid. They are different. Metallic solids are not considered as colloids. Mint chocolate chip ice cream. That's a complex mixture. Gasoline is a true solution. Only manganese is the colloid. The largest particle size is suspension. Therefore, answer is B. Now we talked about colloids and we are moving to colligative properties. I try to explain it in the introduction to colloids, introduction into solution, true solutions. True solutions show, we are now mainly focusing on true solution. There are certain properties of a true solution that are affected by number of solute particles, number, not by the nature. That means if you have sodium chloride or potassium chloride, there are two ions here. There are two ions in sodium chloride. They both have 1 molar solution of potassium chloride and sodium chloride has same number of particles. Therefore, colligative properties, we talked about freezing point depression, lowering of the freezing point of a homogeneous mixture or solution, elevation of the increase in the boiling point are affected by number of particles. So if you have a glucose solution which has same number of particles as sodium and chloride ions, that same number will have the same amount of effect on the freezing point depression, boiling point elevation, and the osmotic pressure. Osmotic pressure, we're going to talk about how it affects when a solute is dissolved in a solvent and separated by semi-permeable membrane. Then the water pressure moving from solution to the higher concentration solution is called osmotic pressure. There are three colligative properties we're going to look into dealing with homogeneous mixtures or true solution. Therefore, one mole only depend on the number. Mole is a number of particles, Avogadro number of particles. When 1 mole of any particle, it could be same number of glucose molecules, same number of sodium and chloride added together, same as number of molecules in the glucose sample. When dissolved in 1 mole of anything, but the number of particles in 10 grams, 1000 grams, boiling point is, freezing point is depressed, depression of freezing point. Depressed by freezing point is 0. It goes down by minus 186 per mole of substance. This is a constant. It's called freezing point depression constant. That doesn't nature, the freezing point depression is same for any substance, only depend on the number of particles. That's a colligative property. Depression of freezing point has some application. During the winters, you add sodium chloride or salt to lower the freezing point of driveways so that you don't get, when you walk in the ice, you can follow. We can use to melt snow and ice, either sodium chloride or calcium chloride. Both are soluble in water, forms homogeneous mixture. Which one is better? This one has 2 particles, sodium ion and chloride ion. Calcium chloride has 2 plus and 2 chloride ion. Therefore, this has 3 particles, this has 2 particles. Therefore, calcium chloride, same number of moles added to ice solution, ice or snow or ice, freezes, calcium chloride is more effective. Ethylene glycol in automobile radiators, antifreeze used in automobile radiators. Also example of using antifreeze as how you use freezing point depression in practical application. The constant we talk about is this. Per each mole of 1 mole, freezing point goes down by 1.86 number of particles. This is the freezing point depression. You can calculate freezing point depression once you know this is called KB. This 1.86, knowing the number of particle size. For example, sodium chloride, number of particles is 2. Calcium chloride, number of particles is 3. So here you multiply by 2 for sodium chloride, 3 for calcium chloride, therefore larger freezing point depression is for calcium chloride. Let's do an example. That's the antifreeze in car radiators. If you had 275 grams of ethylene glycol, what is the freezing point depression? Now you have to calculate number of moles. You get the formula weight of the ethylene glycol, 275 divided by formula mass of ethylene glycol. That's grams divided by formula weight. Yet this is number of moles of ethylene glycol. That's the freezing point depression constant. So you get, this is a negative. Depression is negative. Therefore, freezing point is depressed by 8 degrees negative downwards. Therefore, car radiator doesn't freeze. That's how you do a calculation. Problem. What is the freezing point of a solution dissolving 1 mole of potassium sulfate in 100,000 grams of water? Now, 1 mole of this compound has 3 particles, 2 potassiums, 1 sulfate ion, 2 potassium, 3 particles. Therefore, total number of particles is going to be 1 multiplied by 3 is 3 moles. Therefore, you have to multiply 3, 1.86 negative to get the answer. That's a negative. Lower. That's the negative change. 5.58. That's how much 1 mole of potassium sulfate lowers the freezing point of water. Solution now freeze at minus 5.58 degrees Celsius. Now let's talk about, you can do a calculation for freezing point depression or boiling point elevation. We're going to do that a little later. Let's look at osmotic pressure. Osmosis is when a solution is separated by solvent using a semi-permeable membrane. Semi-permeable means this membrane allows only the passage of solvent. When you separate the semi-permeable membrane, solution and a solvent, solution with certain concentration of solutes, it's a colligative property. This depends on number of particles of solute. The water tend to move into the solution and pressure is higher to stop the flow of water from the solvent side. To apply pressure on the solution side to stop water flowing. That pressure is called osmotic pressure. We're going to look into some of the examples of osmotic pressure in a minute. Boiling point elevation is same as freezing point depression. The constant for 1 mole of solute, boiling point is elevated by 0.53, 0.512. It's a positive elevation, it's a positive change. It's similar to freezing point depression. If you know the number of moles, particles of moles, that multiplied by Kb. Kf is the freezing point. Kb is the constant boiling point. So you can do calculations using either freezing point depression constant Kf or freezing point, boiling point elevation constant. Let's answer a few questions. Which of the following is a colligative property? Molarity is not a colligative property. There are 3 properties we talked about. Osmotic pressure is only one given here. These are concentration limits. We use concentration to calculate the osmotic pressure, but it's not concentration itself is not a colligative property. Which of the following will have the lowest freezing point? When you have a question like this, you have to look at the molarity and number of particles. All have same molarity. There are 2 particles here, 4 particles, ion, 3 particles. Therefore, molarity times number of particles is the number of particles, colligative property, depend on the number of particles. Therefore, aluminum chloride has the largest number of particles compared to other 2. Therefore, answer is C. Which of the following has the lowest freezing point? All have same molarity. But this is a ethylene glycol. There's no ions. They are molecular compound. Therefore, each compound is one molecule. One exists as a one particle. Therefore, they have same number of particles, same molarity. Therefore, all of these have the same freezing point. That's the correct answer for that. Which of the following will have lowest freezing point? Acetic acid is a weak electrolyte. They don't break up in the water completely. Therefore, fewer particles are in acetic acid. Thus, even though solution is having higher molarity, ethylene glycol is one particle. This one has 3 ions. Therefore, 3 times 2 is 6 here. This is not completely dissociated. But this is 1. 1 times 2 is 2. Therefore, this has higher number of particles. Therefore, lowest freezing point is B. A solution contains 1 gram of 100 milliliters. Which of the following solution will cause solution to have the lowest freezing point? These are all molecular compound, one particle. They don't break up. 1 gram is, depending on the molecular weight. This has the higher molecular weight, sucrose. Therefore, if you have 1 gram, there are more particles in ribose. Ribose has the lower formula weight. Therefore, 1 gram divided by formula weight is the number of moles of the solute. Therefore, this A will have largest number of particles. The solution is prepared by dissolving molarity, molar mass is given. So number of moles is 6.72. What is the freezing point depression? Number of moles is this. Therefore, that multiplied by this will give this multiplied by right here. 12.5. So answer is B. We talked about freezing point depression, constant. That's negative answer. A solution is prepared by dissolving 53.5 grams of ammonium chloride. Formula mass is, I calculated. 53 is 1 mole in 400 grams of water. What is the freezing point of the solution? So per gram, per 1,000 grams, that. So this has to be 1 mole. 1,000 grams is 1/8. Therefore, 4 times 186. I did the calculation. Thousand grams is higher depression. 400 grams solution has lower number of solute per 100 grams. Therefore, this divided by 4 is the answer. I said multiplied by 1.86. You get 9 point. Why 2 here? Therefore, each ammonium chloride mole produces 2. That's why this is multiplied by 2. You get 0.93. A solution prepared by 104 grams of barium chloride. What is the freezing point depression? We do the calculation. That's 0.5. Why 3? 3 is number of particles in barium chloride, 3 ions. Therefore, answer is minus 2.79. B is the correct answer. When you look at this problem, they ask in boiling point of this, what is the boiling point? When you dissolve 200. Molar mass is given for the ethanol. That's CH3OH, ethanol, methanol. There's a number of moles. Similar to the boiling point depression calculation. Boiling point elevation is number of moles multiplied by 0.5, 1, 2, 3.5. Now, this is elevation. Boiling point is 100. Therefore, boiling point of the solution is 3.5 plus 100. 103.5. That's the correct answer, C. The solution, these are similar problems. Milligrams, 400 grams of water. What is the boiling point? We done a calculation like that. answer is A. When you calculate this multiplied by there, freezing point depression is lower when you dissolve ammonium chloride. You have to take into the factor now the 1,000 grams is 4,000 grams. Therefore, lower freezing point, boiling point, elevation. When you do the calculation, you get 100.13. So these are similar calculations. I'm not going to go over this. Which of the following is a colligative properties? True colligative property. Which is true of colligative? They depend only on number of solute particles. That's true. They depend on nature of the solute. No. They depend on the number of solvent. It's nothing to do with it. That's just the medium. They depend on the nature of the solvent particles. It doesn't depend on neither solute particles or solvent particles. A is the correct answer. Which of the following parallel properties both members are colligative? Density is not a colligative. Boiling point is. Vapor pressure is colligative property. We didn't talk about it. I initially said we are not going to talk about vapor pressure lowering, depression. So osmotic pressure is also colligative property. Solubility is not a colligative property. Freezing point is. Therefore, B is the correct answer. A solution is formed by dissolving 1 kilogram of water. 1 kilogram is 1,000 grams. Therefore, same boiling point, elevation constant. Highest boiling point, highest number of particles. They are same number of moles, but this has 2 particles. This has 1 particle. This has 3 particles. This has 4 particles. 4 sodium ions, 3 sodium ions, 1 phosphate. Therefore, highest boiling point is shown by D. Which solution has the lowest boiling point? Similar question. Now lowest, least number of particles is glucose. Now that's right now 1 particle, same molarity. Therefore, B is the correct answer. Compared to pure water, one molar sugar water solution have lower evaporation. That's correct. Lower boiling point. That's correct. Freezing point is boiling point is higher. freezing point is lower. Higher wave pressure is not right. Higher boiling point, that's correct. Higher, lower. This is not right. Lower wave pressure, that's correct. Higher boiling point. That C is the correct answer. Let's talk about osmotic pressure. Osmotic pressure is when you have a pouch made out of bladder, bag. Bladder is considered semi-permeable. If you make a pouch and attach a tube into this, and you have a solution of homogeneous mixture inside the bag, and put in the water pushes up water level. That water is the level, this pressure, like a gaseous pressure in Torricellian barometer. When you measure the pressure of gases, this is the pressure column of this water length is caused by the osmotic pressure. Net flow of the water continues until this level is reached. This is one way to find out osmotic pressure of a solution. Semi-permeable membrane is a membrane which have tiny pores. When you have a water solution of true solution made out of water, this tiny pores only allows water to pass through. Therefore, pore sizes are the one that create the membrane. Semi-permeable membrane has pore sizes which are comparable to size of water. But highly solvated ions cannot pass through. Therefore, water will only pass through towards the solution side. Osmosis is defined as the movement of solvent particles through a semi-permeable membrane from a region of lower solute concentration. You can have two solutions separated by semi-permeable. It could be water or lower concentration. This is higher concentration. Water flows from lower to higher. That's the process of osmosis. Osmotic pressure of the solution is pressure. I looked into that in the previous slide. The height of the water column that are required to prevent the flow of water molecules from lower concentration to high concentration. Osmolarity is a term that we use for ionic compounds, where a number of particles are more than one, like sodium chloride. If you take 1 mole of sodium chloride, there are 2 particles. Therefore, osmolarity is molarity times number of particles that give. If you take 1 mole solution, osmolarity of 1 mole sodium chloride solution, osmolarity is 2. molarity times 1 times 2 is 2. Osmolarity is molarity multiplied by number of particles produced by each formula unit of a solute. Some of these ideas are used in healthcare industry. If you take a sodium chloride solution, which is 0.89% by weight, that's what we call a saline solution. It has 0.89 weight by volume. What is the osmolarity of this solution? Now you have to calculate the molarity. We done conversion of weight by weight percent to molarity. So first you have to find how many grams of sodium chloride, that W is in the sodium chloride. This is the weight by weight, means 8.9 grams of sodium chloride are in 1 liter solution. Normally 0.89% volume by volume sodium chloride is the concentration of a sodium chloride used as a physiological solution, saline solution. This is weight by volume percent. How do you get the molarity of the sodium chloride? Normally weight by volume percent multiplied by 10, 0.89 multiplied by 10, you get 8.9. That means 8.9 grams in 1 liter solution. Why multiplied by 10? Percentage is 100. Percentage is 100. Liters are 1,000. Therefore, convert 100 to 1,000. You have to multiply by. Therefore, sodium chloride in the solution is that converted to moles. You get 0.15 moles on 1 liter. Therefore, molarity of the sodium chloride solution is 0.15. Because sodium chloride is ionic compound, it dissociates into sodium ions and chloride ions. Therefore, osmolarity, molarity of the solution for colligative property determinations had to be multiplied by 2. Osmolarity of 0.89 weight by volume solution is 0.30 osmol. Osmol is molarity as well. Let us do a few problems. A hypotonic solution, osmotic pressure has lower or higher than body fluid. Hypotonic is lower concentration. Hypo means low. Hyper means more, high. Therefore, hypotonic has lower. B is the correct answer. If cells are placed in a hypotonic solution, hypotonic means higher concentration. What will happen to the cells? Cell will shrink. When the cells shrink in a hypotonic solution, that called crenation. Let's answer the question. Water diffuses out of the, this is the correct answer. This hemolysis is when you put in a hypotonic. Therefore, answer is water. C and D are not correct. B is the clination when the cells are put in hypotonic solution. If the cells are placed in isotonic solution, equal flow from cells to solution. That's the correct answer. If two solution concentrations are, first one is low, so this is higher. During the osmosis, net flow is water from the dilute solution to the concentrated solution. D is the correct answer. Let's answer a few more questions. This is about clination. Clination is a red blood cells occurs when the placed in hypertonic. That's what we said. This is the correct answer. If you have five point 0.5 molar solution, we talked about saline solutions is 1.89 weight by volume. Therefore, this is less than that. 8.9 is greater. Therefore, this has to be cells have this when you saline solution. Therefore, this solution is hypertonic. 0.5 is less than 0.89. C, the correct answer. 0.5, 5.0 now is higher. It should be higher than the concentration of cells. Therefore, it got to be B. If you have 0.8 magnesium chloride solution, now you have to calculate the osmolarity of the magnesium chloride solution. How do you calculate it? This is 8.0. Therefore, multiplied by 10, you get 8 grams per liter. So 8 grams per liter solution has 0.83 molarity. Since there are 3 ions, one magnesium and 2 chloride, this is multiplied by 3, you get 25. So osmolarity of a sodium chloride solution was 0.030. We calculated that. Therefore, this has to be a hypertonic. This is low. This solution is hypertonic. That's how you get the answer B. We get the following solution is hypertonic with that. Do you have questions? You compare these solutions. Find out which is hypertonic. This one is not. Sodium chloride isotonic solution is, we talked about here, 0.89 on the top. This is hypertonic for sure. It's more than 1.89. That could be the answer. So to make sure that you understand you are given a hypertonic solution, you can go there and get the answer, which only one of them is correct. B is the correct answer because it's 0.3 is 0.30 is the isotonic. This is high. This is why it's become hypertonic. I did the calculation for glucose. Glucose, I used this solution. This multiplied 3.2 multiplied by 10. That's how many grams are in 1 liter of solution. Then you convert it grams to moles. 32 divided by 180. Molarity is 0.18. Osmomolarity is same as molarity because there's no breaking up in the solution. Therefore, this 0.18 is low value. Even if you calculate for 4.1 solution, you get 2.7 something. Therefore, still lower. Hypertonic solution is B. Red blood cells are placed in a solution and the cells become to swell. When they swell, that means water going into. Solution should be hypertonic. Solution has more water. Therefore, water goes into the cells, eventually create hemolysis, breaking up of the cell. Let's answer a few more questions. There's a diagram given here. There are two solutions, A and B. That's the beginning. This solution is A is 10%, 20%. 20% is, therefore, water should flow from here. When water flows, this level goes up. What water levels in the final level? Therefore, A is the correct answer. If it was other way around, then this is the correct answer. In this case, this is the initial solution. This is lower concentration, 10%. This is 20. Water flows. Which of the following solution has the highest molarity? These all have same molarity. Osmolarity depends on number of particles. This sodium chloride breaks up in water to 2 particles, 3, 4 particles. Aluminum chloride, 4 particles. Barium chloride, 3 particles. Therefore, highest number of particles are here. Therefore, 0.10 multiplied by 4 is the highest molarity. Therefore, answer is C. Which of the following has highest osmolarity? Similar question. Now their molarities are different. Therefore, osmolarity is here is 0.40 multiplied by 2. This multiplied by 2. Osmolarity is here is 0. Barium chloride 0.15 multiplied by 3. This is 4.5. Therefore, B is the correct answer. I calculated. I didn't calculate it. They multiplied by 0.15 multiplied by 3. This is 1.5. Next question. What is the osmolarity of this solution? We talk about it. The number of grams of weight here is 10 times. 10 times 3.3 is 33. Formula weight is 164. Therefore, when you multiply it by 4, osmolarity is molarity multiplied 4, you get 0.80, which is the answer C. Which of the following aqueous solutions will have the highest osmolarity? If you look at this, these are same molarity. These are all covalent compound that doesn't break up in the water. They have all same. Therefore, they all have the same number of. This is number of grams. They already calculate the same molarity. They don't break up in the solution. Therefore, they have the same molarity, same osmolarity. Which of the following occurs when the blood cells are placed in hypertonic? Hypertonic means concentration higher. Therefore, draws from water is passed from cell to the outside. When cells is passed to the outside, it becomes smaller. So A should be the answer. This is hemolysis in hypertonic solution. Which of the following occurs when red blood cells are placed in hypertonic solution? That's hemolysis. Which of the following occurs when red blood cells are placed in isotonic solution? None of these. Which of the following is associated with desalination of water? Desalination is salt water applying pressure forcing the reversing the osmotic process, reverse osmosis. That's the answer. Which of the following isotonic is? We talked about this. This is the saline solution of sodium chloride. Molarity is 0.15. We also talk about the sun, the same weight by volume. This is the same solution converted to weight by 0.3 here. 1.5, 0.15 multiplied by 2 is 3.3%. 0.3. Okay, this solution is isotonic because osmolarity is same as saline solution. This is not. This has more if you calculate it. That's going to be 10 times aluminum chloride has more particles of ions. Therefore, that's going to be hypertonic. Answer is B. Let's answer this question. Glucose, isotonic to, I did the calculation. You calculate the osmolarity of 0.15. This is 0.3. Osmolarity of sodium chloride 0.3. This solution should be, glucose should be 0.3. Therefore, we convert grams to moles to grams, you get 5.4. This is the answer. You are converting back and forth from molarity to, that's how I got 0.55. Which of the following solution isotonic to osmolarity is 0.30 molar here. This has 3 ions. Therefore, this should be 0.3, has 2 particles. This cannot be because it is larger. Probably A, B. How do you calculate this? There's 3 particles. 0.3 is equal to, which of the following solutions are hypertonic? That's A is the correct answer. This is isotonic solution. This is hypertonic solution. Which of the solution isotonic was that hypertonic is this. C the answer. Saline solution has weight by volume 0.89. How do you prepare 1 liter iso? Suppose you want to prepare, what mass would be you needed? I didn't do the calculation. I will put that in the slides. Isotonic saline solution is 0.89. 0.89. That calculation is not done. What is that promise? Residual concentration of drinking water produced by is very low. 0 is not correct. 40 is in somewhere around here. C is the correct answer. Reverse osmosis is used to separate sodium chloride from water, and you can get fresh water. Hemodialysis is a process where blood is purified in patients with impaired kidney function. The machine, blood in here and the blood out here, is passed through membrane like this, blood in and out. Blood retain platelets in the process and remove urea, salt, waste compounds in the blood. Therefore, person get clean blood. Kidney function is similar to capillary dialysis, artificial kidney. So therefore, it's similar to osmosis, but you can create dialyzer membranes just to, pore sizes could be manipulated just to let the urea pass from blood to the urine. That's about the dialysis. Let's answer. When you look at the question here, 308, why is the osmotic pressure of the dialyzer to prevent the loss of glucose from the blood, to prevent, I think it's not prevent sodium and both. It removes glucose, to prevent loss of sodium, prevent sodium loss and glucose loss. But the urea is passed. Which of the following is true when comparing dialysis membrane to osmotic membrane? Both membranes allow solute particles to pass through. An osmotic has larger opening. Than dialysis membrane. Both membrane allows solute particle pass through. An osmotic membrane has larger opening than dialysis. To me, it looked like A. Both membranes allow solute particles to pass through. I'm not sure about larger opening than dialysis membrane. None of these. So they are completely different. Which of the following is true when the comparing dialysis membrane to semi-permeable membrane? Both membrane allows solvent to pass through. Oh, this is solute. Dialysis allows, I was reading this as solvent. Therefore, all are not true. Which of the following in problem 310? Both membranes pass through. I'm not sure about this. Both membrane solvent pass through an osmotic membrane, larger opening. I'm not sure about that. A should be the correct answer. Which of the following pass through a dialysis membrane? Small solute molecules. Macromolecules, not pass through. Colloidal particles. This should be the one. Colloidal particles are larger. The greater the number of dissolved particles in solution, lower the osmotic force. Greater the number of solute particles, greater the osmotic pressure. Pure water has osmotic pressure of 1 atmosphere. False. Pure water don't have a pressure, osmotic pressure. Now we are done with chapter 6. Already here.
Yes, sir.
All right. I will see you on next Monday.
Yes, sir. Thank you.
Yeah. You guys have a great day.
You too.
Thank you.